Good morning, everyone. Welcome to one topic, one many simulations and many learnings. So this is my sixth video, and this video will be focused on the SWOT equations. That is the application of kinematics on uniform velocity motion, uniform accelerated motion, and if possible, we'll look at the variable acceleration. Also, I didn't find any tool. Anyway, let me just find it. Okay. So let me just share my screen, what possible things that we can do from here. Okay, this exercise is only to make it clear for the students, like when they arrive at a problem, now can we put that problem in a visual way? Okay, can we see that problem? Can we visually are we able to visually observe that problem? So that is what it is about. So towards it, let me just share my screen. There are some web-based tools which are available wherein we can translate the same problem to visual means, and thereby we can understand this. Okay. The first thing is that let me come here. Right. The first one is, before we start with our what you call SWOT equations, we initially describe what you mean by one dimension and two dimension. Two dimension is nothing but your projectile motion. One dimension is nothing but the coordinate actually changes by only along the x direction or along the y direction. Now towards it, now let me show you. This is one of the biggest confusion which many students have it. Okay, until unless they do not understand the differences between one and two dimensions, it will be very difficult for them to do anything on projectile motion. So therefore, first thing is, this is better that we do this one initially. Okay, now let me click on 1D here. This is the URL. I'll just put the URL in the description of the video. Okay, now if I click on 1D here, now let me tell you what all we can do from here. Now, see, I will be able to move this along the x-axis. Okay, I have moved it from x equal to 0 to x equal to 22. But if I try to move it perpendicular to this, or if I try to move it away from it, you see, I'm not able to move it. Okay, though I hold my mouse cursor and I keep on doing this over here, but still I'm unable to move it over here, which means there's a constrained motion, which tells me that the particle can move only along one direction, only along a straight line. Okay, this is how this can be introduced. Now, when I say about a two dimension, I can click on this one here. Now you see an x and y axis over here. So now I can change in any direction. See, I can move it in a curve. I can go like this. I can go like this. I can go wherever I want. So as a result of it, this is your two dimension. Now when I say about two dimension, what does this vector indicate? This vector indicates your position vector. That means every point will have two coordinates, x and y coordinate. I can mention about all these things. Okay, this is where this kind of software tools are being very much useful. Okay, let me go on to the next one. This is useful only for so much to understand about what is your position vector and what do you mean by one dimension, what do you mean by two dimension. A very simple thing, but really a powerful one for the students to make understand the differences between one and two dimension. One dimension only along one axis. Two dimension, it can be on both the axes. It can move along the x-axis, it can move along the y-axis, or it can move in the space between x and y-axis. That's how you can indicate your. Then comes the next one, uniform acceleration. Now what I can do is I can make this one to work with uniform acceleration or uniform velocity, both. So I will make this to be acceleration to be 0 initially. I'll make acceleration to be 0. So here a equal to -5 over here. Let me make it a equal to 0 first. 4.9, 4 point minus 2.6, somewhere in the middle. 0.1, 0.2, 0. Okay, and now what I'll do is I'll keep this one to be at 0 here once again. If I keep it at 0, so this tells me about how do you actually take the origin, how do you take the displacement. Displacement on the right hand side is taken as positive, and those on the left hand side is taken as negative. So therefore, if I want this car to be pulled over here backward, so what I can do is I can move the displacement like this. Okay, so what does this tell you? The initial value of the displacement is going to be minus 4.6. And the velocity, let me keep this at somewhere around 1 here. Okay, if I keep it at 0, and we ask the question, what will happen to it? Okay, and when I run this, you see the car does not move. The time slider is moving, car is not moving over here. But if I keep this at something like 1 meter per second, then what happens to the car? Okay, I can say that the car is now moving, but with an uniform velocity, right? I can also ask about how do you determine the uniform velocity? What is a curve of VT graph comes and gives you across. So when you are teaching about this one, you can together teach even the graphs also. So it will be very useful for them. okay, to understand both of them. And then we can also show something like, after this, okay, you can start with your acceleration. Okay, you can take the acceleration over here, or you can put the acceleration like this. And let me reset this first. Let me reset this. The car is over here. Let me run this over here. So now you can say, if the initial velocity equal to 1 meter per second and your acceleration is 0.8 meter per second square, then what will happen to the car? Okay, how does it move? Okay, now if I say that, then both the velocity and acceleration vectors are in the same direction. That means velocity is increasing, thus the car moves in the forward direction. And the equation here is given over here, and the graph is being given over here. Everything is being shown over here. And you can then ask the question, why do you get this negative intercept? What is the reason for this? How do you make this positive? Why, when will it start with the origin, right? There are so many questions we can ask. Okay, now let us say, for example, if I make this V0 to be equal to something like 3 meter per second, and A to be equal to something like 0.2 meter per second square. I'll do one thing. I'll make this negative. I'll make this as around minus 0.3. And then when I start it, okay, then what will happen? Is the car moving in the forward direction or in the reverse direction? I can ask them. Then you see that, okay, the car is still moving in the forward direction. That means you can very clearly tell them that the direction of velocity and the direction of displacement is along the same direction. So as a result of it, it's going. But you see the velocity of the car is slowing down, and after some time, what will happen? It will come back over here. As you keep on saying, see, now V0 has also become 0. Now it is reversing its path. Okay, it's coming back over here. The equation demonstrating this is equal to so much, and you can still ask them, at what time does it take the reversal? You can ask that question also, right? So therefore, so you can ask many questions based on these kinds of softwares. Okay, and now let us move on to the next one. So I'll move on to the next one over here. So this gives you something like two object system. Okay, in a two object system, that means this could be some problems like you had a problem recently, maybe 2 years before also we had one problem, wherein a police and a thief, both of them start at the same point, at the same origin, and at t equal to 0, both of them start. The thief was moving out with an, with a uniform velocity of 5 meter per second, and the police, the moment he saw that, okay, the jeep actually started to overtake him with an acceleration equal to 0.5 meter per second square. And what time does he actually catch them? Will he really catch him or not? Okay, questions like this can be asked over here. Okay, so what you can do is you can say at t equal to 0, both the police, let me assume the police is nothing but a blue color car, and the red color car is a thief. Okay, both were initially at the same position. X0 here, X0 is equal to 20 bit, X0 equal to 0 here. I'll make this as 0. Okay, I'll make this as 0 over here. Now, when the red car moves past the police car, let me assume the red car was moving at a velocity of 20 meter per second. And the moment he determines, okay, he's moving at 20 meter per second, we'll do one thing, we'll do realistic ones instead of taking 20 meter per second. So what is the max velocity that the police car actually stops us? Let's say it's at around 80 kilometer per hour. Okay, I'm going on a highway, and if I cross 80 kilometer per hour, then definitely the interceptor stops me and I've been fined, right? Okay, the max speed that I can go here is only, let me assume, 60 kilometer per hour. Okay, but I am going at 80 kilometer per hour. Now, if I am going at 80 kilometer per hour, now how do I convert it into meter per second? See, it's in meter per second, right? So let me go back to my calculator. Now, 80 kilometer per hour, I need to convert it into meters per second. So this should be 80 multiplied by 5 divided by 16 will be around 25 meter per second. So what I will do is, I will keep this car to be at 25 meter per second. And this is at 0. Now, as a result of this, immediately the blue car will have an acceleration of, let us say, around what is the acceleration? What is the pickup of a car? Okay, you can discuss these kinds of questions. So let us say I have a jeep, and the jeep starts from 0 and has an acceleration of something like around 30 kilometer per hour. Okay, 36 kilometer per hour. Let me see. If it is 36 kilometer per hour, then 36 minus 0 divided by kilometer per hour will be 36 into 5 divided by 18 will be around 10. 10 divided by 1. So it will be 10 meter per second should be my acceleration. I'll keep this acceleration to be around 10. And the police jeep initially was at 0. This is 0 over here. This is 0. Now with all these parameters, and the red car did not have any acceleration. It was moving with the same velocity. The acceleration 0 here. Okay, now let me run the simulation and see where is this red and blue color. Both the car are at the same point over here, right? Now both of them are now starting. Now let us see when do they meet. So how do I understand where do they meet? The curves should intersect at some point. Let me run this. Now you see, blue car is lagging. At some point they meet over here. What is the point it meets over here? It meets at this point over here. What is the point? It's at 4.5 seconds away. I can meet over here, right? Okay, so therefore, now after that, what happens? So you see, this is now crossing a larger distance, and this is lagging behind the same distance, lesser distance, right? So therefore, okay, and as a result of it, you can see it meets at this point at a distance of what's the distance over here? 120, 122, 124 meters. At a distance of 124 meter and in a time of around 5 seconds, I'm definitely able to meet the thief. I can catch hold of it, right? So these kinds of questions can also be asked using this. Any kind of complex questions which involves two objects which has multiple velocities, multiple accelerations, so on, you can put it across here and graphically you would be able to solve it, right? Okay, then, but don't take the area here. Area will not give you anything here. Next one is motion with constant acceleration. Okay, let me reset this. Let me start. So again, this one also, it tells you about, okay, what is the displacement time graph, what is velocity time graph, what is acceleration time graph. I can change the parameters and I can ask it to show the velocity vector, acceleration vector, okay, as the car moves, and I can also show the graphs correspondingly. So usually we know what is a velocity vector. What I will do is, so this initial vector is 0, initial position is 0, initial acceleration is 1 meter per second square. Let me start this. See the red color vector you can see here. This is nothing but a velocity vector. Slowly it is growing up. Why is it growing? You can ask this question. It is growing because there is an acceleration, right? Now you see, so we have got the graphs over here. Ex versus t is giving a non-linear curve like this, and then v versus t is giving a straight line like this, and a versus t is giving rise to a constant one here, right? So which tells you it's constant acceleration. Thus we are able to answer questions based on this also. Okay. Now let me move on to the next one. These are not very complex ones. The same things you can achieve it in the previous graphs also. The next one, PHET. This is really good. Okay, I like this one. So I have tried this in my classes also. So what we do is, so you have two tabs over here. One is your introduction tab. The other one is this one. So you can pull this man from here and pull it up here. Oh, there's something running behind. Let me stop here. Let me stop here. I'll reset here. Reset all the settings. And then why? Okay, something is running behind. I'll refresh this. This is the problem with it. So what happens is sometimes when you download this one, it's more easier. Otherwise, you have this cheer PJ running, and after the jar file gets loaded, it takes some time graphic system to get initialized, and after that you get the address. Okay, so now anyway, for me, luckily I had started this earlier. Now anyway, it is getting instantiated and it's moving now. Okay, now we get this over here. Now I can move this fellow here. Okay, I can move it to hit this door. I can say the position of this person is so much. I'll keep it at 0 here. And from here, I can change the velocity. I can change the acceleration. I can do whatever I want using this. Okay, I can do it from here. I can click on this. Nothing is changing. So what I do is, I can now change the acceleration vector a little bit. When I do this, what happens? The person is now moving from one end to the other end. As time proceeds, his velocity keeps on increasing. The value of the velocity can be noted down here, and then the value of acceleration is also given here. Okay, so therefore, you can ask the student to take these values, plot a graph, okay, get the data from here. Data collection can be done using this very easily. Now, when you go to charts, you can see what's happening to the charts. When you click on this, okay, so here nothing is seen. So what I will do is, I have to change the acceleration, velocity vectors and so on. Let me change this a little bit. Okay, now when I change this, now you see, okay, there's a different tab. There's a different set of simulation, which happens over here. The graphs of ST, VT, AT graphs can be observed over here. Now here what I can do is one more thing that I can do. See, the person is now just moving in this direction, but I don't want this. I want this person to move from one edge to the other edge and again come back to it. I want to make him keep on oscillating. Now how do I do this? So towards it, what I can do is I can go to this special features. Let me halt this. Let me go to special features over here. Click on expression evaluator. And I have something like 7 sine of t plus 2. I can change any equation here. Okay, it's not that I should always have this one, But for time being, whatever is by default, I'll take this value, and then maybe I'll change something here. I'll do one thing. I'll just make this as -2 here, -2. Okay. And then when I run this, now this person is going here, then he takes a turn once again. Now, if you observe him closely, he starts from here, goes to one edge, again comes back, and he keeps on oscillating. Now, you can ask your students, why does this happen? What is the reason behind it, right? Okay, this is 7 sine of t -2. So, as the value of t changes, okay, the value of sine of t also changes. And as a result of this being a periodic function, which means the displacement of the person also keeps on changing. So, that's how the acceleration changes, and this changes, everything changes. Now, you can ask the question whether the acceleration is seen to be a constant, is the velocity constant. See, from here they can understand. But same time, okay, by looking at this equation also, you can see, now the person is moving in the opposite direction. Earlier it started from here, now it went like this, he came back like this over here. So this keeps on changing forever, right? So like this, you can understand more about the non-linear motion. This is completely a non-linear motion. And now you can ask whether it is an acceleration is a constant or not constant. So you can get to know that the acceleration is not a constant. See, it's kept on varying over here. See, it's not indicated by a straight line. It is being changing like this. Then you can ask, can we use equations of motion for this? You cannot use the equations of motion because the Stewart equations can be used only when the acceleration is a constant. Okay. Now let me move on to the last. Now this is relative motion. Relative motion, you actually don't have it in your syllabus, but it's good. Okay, if someone is preparing for the NEET examinations or any competitive examinations, AP physics or anything like this, then this would be really useful. What we do is, let me click on relative vector, show velocity vector. So what is relative motion? There are two velocities. Okay, the object is supposed to be having. The first velocity is the velocity of the boat, which has been having like this. The second velocity is the velocity of the water, which has been flowing or drifting across in the river. Now the boat has to cross from one end to the other end, okay, along the straight line. Now, if that is the case, if it goes straight like this, will it reach this point? No, right? It will never reach that point, and it will definitely take a turn like this. Let us see what happens over here. So in the aim direction is 0 degrees. You have all this. If I click on run, you see it takes up this velocity and moves and joins it. Okay. Now what I do is let me increase the velocity because I'm going with a very slower velocity. This is what happens. Now let me increase the velocity. If I increase the velocity to this much, and I ask the question, velocity of river, sorry, this velocity of river, right? I keep the velocity of river to be same. This I'm not changing. I want to increase this velocity, the velocity of the boat. Velocity of the boat relative to river is 4 meters per second. Let me make it higher. Okay. Now, if I make it higher, do you think where is the boat landed over here? The boat landing is not seen. Okay. So if I increase this, then do you think it will reach this point because it's going faster? Let us run this also. Now, once again, since there's a velocity, it will land once again here itself. Okay, it will not change. Okay, or maybe it may reduce. Okay, now it is here. If I reduce this to something like 3 meters per second, or maybe half of it, lesser than this, it was at this point. Let me run this. Now see where does it land? Earlier it was landing here. Now it is under the mercy of the velocity of the river. It moves and lands at a farther distance. So therefore this you can explain. Now what should I do if this is the case? Now what I will do is I have to change the direction of the boat. Since it is being going like this, okay, initially if I start with this direction, what will happen? It will be moved like this and may land over here, right? So let me move this backwards here. I do it like this. Okay. When I do this and run here, now what's happening? Actually, it was landing here. Still, it is going in the same way. Right? Maybe my speed is much lesser. I'll increase my speed to, let us say, it was earlier 3 meters per second. I'll keep it at 3 meters per second. Now, what I will do is, I will increase this angle a little bit more. This way. Okay. Now, let me run this. It was landing here. Now, what's happening? It is not landing there. I think it is almost coming nearby to it. Okay, so it landed here, which means I should still increase the angle here. So if I keep it somewhere over here, right, and run this, will it land exactly? I think so. Most of the time, okay, it might land over here. Let us see. So slow. No, still it is not landing. Okay, it is making a small difference. Might be it is landing over here. It might be landing over here. Okay, let me keep it a much more larger angle. Okay, now let me run this. Now what's happening? Now it's going like this. Probably I think it may land here, or it may land even before the target. That can also happen. Very slow. Let me increase the speed if you want. Let me increase the higher speed and run this. Now what's happening? It's going against the tide, and therefore it will not come to the target, but instead it may land somewhere else. So what we can do is we can ask the students to prepare something like a graph for different values of the velocities and as well as the value of theta, and ask the question, when does it hit it, and what values of this and the value of theta it will hit it, and then ask them based on this, plot a graph of it, arrive at an equation, and then theoretically prove, okay, how do you prove this one, right? And that will help them out to understand many concepts. They'll be able to understand about what is the, how do you resolve a vector, okay, and what vector should you take to move it in the same direction, and all this information they will easily get it across. Okay, so this is all we have in case of your SWOT equations. Don't have much more than this. The tools which are present generally are like this. Maybe there could be one or two graphical tools available, but anyway, I have not put it over here. Graphical tools generally we use Desmos or anything else. Okay, so therefore we are not putting that. And I think with this we into the simulation that is on SWOT equations. And if you still have any more questions, you can put it in the comments. So tomorrow might be we will be seeing some more. Let us see as much as possible. I try to cover almost all the concepts using this simulation tools. Thank you for being with me. Do share, like, and subscribe to my channel for more such updates. Thank you.